Hey, what's up guys, welcome to another video. In this particular video we are going to talk about one of the project that has been done by one of my team member who was actually working with me and few of our Philips teammates. So this video will only teach you about how to fudge in Windows application with one of the really popular tool called as AFL. So the project was about fudging Windows binary. So the next videos that you are going to see is completely about the same explanation that has been done by my friend Karthik Magarajam. In fact, he got great help from Nilesh Swami. Probably few people know him as well. So this particular video is about that particular same project, and yeah, Karthik Magarajam has basically tried to explain everything, like from the basics of fudging till the like how to remediate and all those stuff. So go ahead and watch the complete video and let me know in the comment box if you have any query or how do you like this particular video. Of course, this video is not always recommended for beginners. Probably some people might not find it that interesting, but yes, it will definitely teach you something about fudging if you go about, or if you wanted to learn about fudging in your future as well. So make sure you watch this video and try to grasp all those concepts about fudging. If you like this video, do let me know in the comment box and hit like, share and subscribe.
The project title is Fuzzing Windows Application. The objective of our project is to demonstrate that bugs in code exist post-verification by the compiler and static analysis. The agenda for today's discussion is what is fuzzing, how WinAFL fuzzer works with Windows binaries, how to select a target function to fuzz with WinAFL, analyze the crashes that have been identified by WinAFL, compare the results of WinAFL with Visual Studio Code Analysis results and HP45 Static Code Analysis results. And finally, we are going to look into bug fixing. Now let's see what is fuzzing. Fuzzing is a security testing to identify security vulnerabilities that exist in a software or a hardware system. It works in a way that sending large amount of modified data continuously as an input to the target system to make the target system to crash. Crash is a starting point for any vulnerability because it gives some information about a vulnerability. Fuzzing is responsible for identifying large amount of privilege escalation and remote code execution vulnerabilities. Let's look at how WinAFL fuzzer works. WinAFL fuzzer is an instrumentation guided fuzzing tool. That is, it takes one or more valid files as an input and continues fuzzing by performing bit or byte flips in the input file. We will discuss more about bit or byte flips in the later stage. In case if one of the modified file generates large code coverage, then it will be added as part of the input files list. It uses a tool called DynamoRio to modify the code at runtime. Now let's look at our current working environment. We have downloaded Microsoft application from GitHub and built that application using Visual Studio 2017. Now the build is successful. We have generated our DLL and exe file. So we're gonna fuzz on the DLL and exe. The calendar reader console application is a small visual C++ application that wraps around the calendar lib DLL. The calendar lib DLL has a parsing capability. Already we have set up DynamoRio and WinAFL on our system. Let's look at how to select a target function. We can give any function name or its offset as a target to the fuzzer. But the function should have the capability to perform functions like open the input file within the target function, and it has to parse the input file so that we can measure coverage of file parsing. It has to close the file. This is important because if the input file is not closed, WinAFL won't be able to rewrite it, and it has to return normally. We can calculate the offset of the target function using WinDbg. Let's calculate our target function offset using WinDbg. First launch the WinDbg and open our executable calendar reader. And this is the start address of the binary. Note down. Our target function is main. Let's find out the address of the main. Examine calendar reader main. This is the address of the main. Note down. We need to subtract start address of the binary from the address of the main function to calculate the offset. It is 91,730. This is our offset that we should pass as input to the WinAFL fuzzer. Now we are going to start our fuzz testing on calendar reader binary. Before we start, let's look at the details of each parameter. First one is -i input. Input is the directory that contains all the valid input files that are passed to AFL fuzz. We need to create this input file. We should create this input file under build 32. I'm using 32-bit AFL fuzz. I've built that AFL fuzz under this directory, so we need to create input directory here, and where you can locate this AFL fuzz.exe and winafl.dll. These two files should be there under this directory, and we should pass all the valid input files. Now let's check. We have generated calendar reader binary through Visual Studio 2017. Let's go to the directory and check whether it parses this particular cal file properly and gives us the valid input without any error. For that, let's run this command prompt and calendar reader.exe space cal. That's right. Yes, it gives us the input without throwing any error. It parses the cal file properly. Now the next parameter is -o output. Output is the directory contains all the output generated by AFL fuzz. We need to create the directory by ourselves under this one, same build 32. The next parameter is -d. We need to point Dynamo Rio library files to AFL fuzz to perform dynamic instrumentation. And next parameter is -t, timeout for each run. And -m is the memory allocated for the target process. I have allocated 10,000 MB. You can allocate according to your capacity. The next parameter is coverage module. We can give multiple attributes to this coverage module to complete code coverage. So we are included calendar reader.exe and the calendar lib.dll. Next is target module. The module that contains our target function. Our target function is main. So earlier we have generated a offset for our target function, that is 91,732, 730. We need to include here. And this parameter in is the number of arguments that our target function takes. I've given just 4 we never know how many arguments the function takes. So just given 4, and the first iterations, the number of time that the target function should run before it terminates or it starts a new process, and the directory where we have generated the calendar.exe. Now let's start our fuzzing on this calendar.exe using let's go to the directory where we built AFL Fuzz. Run a command prompt, and we have a command. So just let's run. If you see it is starting, these are warnings you can neglect. So the fuzz is started properly. I have stopped the fuzz testing manually. Now if you look at unique crashes, it is 22, and it has taken 8 hours 33 minutes to generate unique crashes of 22. That's a really good thing. And also this time matters based on the size of the input you pass, and also the size of the binary file, and also the size the memory size you allocate for the target process. And in our case, if you see the speed of the fuzzer is very slow, 41.49 per seconds, so it's very slow, and the fuzzer will just go on for days. But for our project purpose, I've just stopped in the middle, and so we got 22 crashes. We'll analyze the crashes later. Before that, let me explain about the bit flips and byte flips. So for that, let me open our valid input file cal using a X editor. I have an X editor, and open that cal file. So basic cal file, I opened it. This is just for the explanation purpose. And if you see, there are 16 bytes in a row. In case, consider yeah, maybe 16 by 8 or 8 byte flips. Okay, which means the fuzzer will change the first 16 bytes. It will change, it will flip the first 16 bytes, and then 8 byte, and then it will pass as input to the binary to execute it. And then for the next flip, it will just move 8 byte forward, which means 1 2 3 4 5 6 7 8. It will just it'll move 8 step forward, and then flip from here for the another 16 bytes, and pass that as a input to the fuzzer. That's how the bit flips and byte flips work. We can find these 22 crash files under the directory output. That output directory we have created before we start our first testing. This is the directory we have created. If we go to crashes, we can find 22 crash files. Now we need to extract information from these files and generate a report to analyze and to find out whether any vulnerabilities exist in our software. To do that, we have used a tool called Bug ID. It's a very good tool, and it works with Python 2.7, and you can download it from GitHub. It's free of cost. So already I've set it up, this Bug ID. It creates a lot of errors during the configuration, but it's a very good one to generate report from crash files. And also I have created a small Python script to generate a report. So this is the report because we have 22 crash files. It's very tough to generate a report or extract information one by one, so it will be easy if we could automate that. So that is the reason I've just written this one. And let's see how it works. And can generate some already I've copied all this 22 crashes under this results directory now. Okay, so let's go to command prompt, run Python and the script. So just start. It will extract information and will generate report. You could see here it's generating. Yep, it is generating reports. So there were 22 crash files, but it has minimized everything, and it has given us just 4 files. These 4 are unique vulnerabilities. So now let's analyze these vulnerabilities to identify the crash point. Bug ID has generated 4 reports from 22 crashes. So these are those 4 reports. Let's analyze one by one. The first one is generated from crash number 21, and it is a denial of service. It's a security impact, and the description is here: access violation while reading memory at 0 using a null pointer. And the good thing about bug ID is even if there are 22 crashes, so if there are some crashes is related to the same vulnerability, then it will minimize that and it'll give us one report. At the same time, if the particular crash is not leading to any a critical vulnerability, it will not give us a report as well. So the next one is giving us same detail: denial of service, that is generated from crash number 15. And the third one is generated from 11, but it is a potentially exploitable security issue. That is good. The final one is also same, potentially exploitable security issue, but that is generated from crash number 19. And bug ID also gives information about the assembly. Since we have a source code, it will match and give us assembly as well. And it just gives further details and the line number, the current instruction that has caused where the crash has happened, and also the return address it gives. Since we have source code, we can match the crash instruction with the source code by using WinDbg. Look at how. So let's launch our calendar reader. Okay, we need to pass argument. Let's pass the argument here is crash number 19. Results crash number 19 in this folder. Yes. Let's run it. Since we have source code, it has fetched the source code and is given us the same instruction where the crash has happened. To analyze further and to get more details about the exception, we can use analyze hyphen. We can use verbose and analyze. So it gives us the exception details and more information. So in this, it has given the same source code in the line number 238. Yes. So the instruction. So let's look at the input file that we have passed to the fuzzer, and the input, input it has generated the crash number 21 it has generated. Let's compare that, and which bit or byte flip has caused this instruction. So we can use any X editor to compare those two crash files. Input file, the crash file, this is the basic file, the input file that we have passed, and Arvin AFL generated crash number 19. So from this results, the crash number 19. Yes. Okay, so now let's compare these two files to understand which bit or byte has flipped, that has made the system to create a crash. So any other changes in this one? No change in the crash file. So from the original file, it has changed the byte, first byte from 26 to 2F. It has changed, so that byte flip has caused a crash, as well as a few other bytes. But this is a major problem. This is a unique byte that has caused a system to crash. Now I've just run a scan using this Visual Studio to identify whether it is throwing any kind of issue related to the line number 238. It doesn't throw or give any kind of vulnerability that is severe or potentially exploitable. And so I've used HP 45 to run a scan, and it has given me this particular issue as a memory leak. So before that, I would like to explain that this particular point is called as a source, and where the input enters from HTTP request or from database. Okay. And this place is called as a sink, where the information will be executed after the processing. This is all the steps are like the flows where the data where it goes around the application. So it enters here, and then it goes to this place and performs some actions like that. It will be keep going, and at the end, this is the place where it will be executed. So in our case, I've just gone through the code and identified that line number 761 here, they have the memory has been initialized to a variable, but that is not released at the line number 1116. So this has led to us a memory leak vulnerability. And so 45 has identified this as high vulnerability. If you see, look at the category, this is high, and the solution for this vulnerability is to implement forward-reaching go-to statements, so that the function as a single well-defined region for handling errors. So this is the fix for this memory leak. So the objective of this project is to perform fuzzing on Windows binaries to identify issues that hasn't been identified through compile and Visual Studio Code analysis, and to analyze the crash point and identify which byte of bits causing a problem, and also go in little bit detail about the fuzzer. So we could run the fuzzer for a few more days, because usually fuzzer takes a longer time to identify issues. So I have performed around 5 to 6 times on the binaries. So few times it was just keep changing. The results were like, sometimes it will give me a double free vulnerability, and sometimes integer overflow, and recently it has just given us memory leak vulnerability. So if we could run for 2 more or 3 more days, we can end up with very good vulnerabilities, maybe more number of vulnerabilities. So that's it, for this project I've done, and thank you so much.